correct? Minus. Now, the same thing in our code is what? This is what? The difference between them, all right? J to J minus 1. We take the difference between them, all right? And then we divide it with some temperature. The same concept, all right? And we take the exponential. So therefore, let's see. So the similarity, how they did it is the following, okay? So we start and we say the following, that the temperature, this is the original equation of Boltzmann, all right? So I will use Boltzmann distribution, this one here, exactly this one, in order to select whether a new state is acceptable or not, all right? Or whether the step is acceptable or not, first of all, all right? So, however, the probability, if I were to accept it or not, okay, the acceptance of this thing, all right, okay, is going to be only one thing, okay? The probability of acceptance will be determined by this factorial, this function, that I actually write it a little bit different in order to ensure that it's going to be between my boundaries. So delta divided by t. So look, this is exactly the same function here, all right? This is how they did it. And we say that, remember, delta, all right, we try to make it positive, okay? And delta and t are positive. So therefore, this probability is between, if you see the calculation, is what? The maximum is what? Is 1 plus 1, all right? It is 2, so it is 1 over 2, it is 0.5. So the probability, the number, the value that this can take is from 0 to 0.5, okay? Of course, smaller temperatures, they will lead to act to smaller acceptance probabilities. Okay, so remember, as the temperature goes, think about the equation. The temperature goes down, let's go up here. So we squeeze it to the left. You see that? So the same thing here. As the temperature goes down, so this T, we cool it down, all right? Then what happens? Delta over T does what? Goes up. So exponent of this thing goes up. So 1 over 1 plus exponent goes down. You got it? So this is how it works, okay? So at the same time, so therefore the probability becomes lower to accept it. At the same time, look, if you go to larger delta, if your delta is very high, so if you do a too big change, all right, then again, it will result to a smaller probability. That's all. This is the criteria, actually. Someone may say, why so complicated? Folks, it has to do with the behavior of the system. How is your function and if it makes sense, this thing, all right? In some cases, simulated annealing will fail, all right? As gradient descent, as whatever, as the ADAM version is going to fail. So therefore, that's because people do studies, and that's because when you go and work to a place, they will tell you, here are the algorithms, the tools actually. Here it is, plug in the numbers and give me the results. All right? Because someone has gone through the analysis. And this is, I open a parenthesis, and that's because it is important for you, and I think that this is important for you to learn it, because this is most of the power as a computer scientist is to optimize the optimization. Otherwise, you are just operators, all right? You don't even need to finish, graduate school to run algorithms. Just push a button, all right? So think about this, guys, okay? It is very important. I know that many of you, like last Tuesday, in the class were only 13 people out of like 67, however we are. And I say that clearly. We collected names, and these people are going to have a huge bonus in the grade, all right? Because your job is to be there, okay? And your job is not to sit at the back and just type and solve other problems. If the presentations and the material is not appropriate for you, of course, you don't like them, or it is not what you are seeking for, yes, don't come. But if you are there, okay, embed yourselves, learn it, because at some point, your power as computer scientist is not to run a computer. It's not to just plug numbers and give numbers back to someone else. It's actually to think how to optimize and how to these processes. Okay, that's it. Okay, even for people that they don't go for a PhD, this is very, very important for you guys in order to know how to select something. This gives you far more power than just plugging numbers to a software. All right. Okay. The reason I say that is because whatever I do, any one of the instructors in any programs on the planet, if you do not care, there's no way to make you to care myself. But you will see, as you realize right now, that the market is changing drastically. All right, pretty soon there will be software robots doing this job. All right, so you need to think how to adopt. And one way to deal with problems is actually to become powerful. That's all. And this means study, nothing else. All right, so let's see therefore some ideas here. Let's go back to the issue of the simulated annealing and see what does it means, again, the options and how can we change things, all right? The question is here, something that maybe it was not very obvious is that we change T, all right? In every step, it is the T that changes. So the question is, how do you change T? That's the other question, all right? So you can actually have different ways of changing T. And here is where you can actually come up with great solutions, and actually your the third and final assignment will be actually on this thing, all right? How to change T. That's all, okay? All right, so what else? Any questions so far? I think that you should have many questions eventually as you start reading this thing, right? Now, the big question is the following, therefore. So what do I do in order to push this thing? Well, every time, how does this thing work? We change the temperature, all right? We give a high temperature at the beginning, okay, all right? And systematically, we start lowering the temperature. What? The T on the equation here, on this thing here. All right? So the question is, how then it works? As you cool it down, you store the best solution. Okay, this is the trick here part. So therefore, allows you to keep a track of these things and go back. Okay, in order to improve it. Okay, so one how to say way, there are many equations of change, and then you change systematically the T. So let me give you some ideas. There are many schedules. You can actually even do a linear thing, all right? So there are many schedules, as an example, that T can change by, you have a basic, I don't know, let's call it T naught, and you have an M, and this M here, it is the step that you may use in some cases. In other cases, you can even put this thing on a power. You can actually do, let's say, T times some other number, some A, and this on the power. This thing actually, it is part of how you reduce this thing. So you see, this is actually, remember, part of the stochastic search and so on. It's actually the trick, how to select this step. Okay, so the Boltzmann distribution removes part of this guess and makes it natural. But still, within the Boltzmann distribution, you have to change the T. All right? If you go too slow, you couldn't find a very good solution. However, there's a good chance you're going to take it too long. If you go too fast, you may actually trap yourself in one of these minima. All right? That's all. So it works a little bit differently. All right? Now, so the question is, are there, how to say, other notes about it? I'm going to go a little bit later in next session on more details, but the idea is also that not only we go down the temperature, but we can also do what? Go up. Heat up the thing. All right? By doing the heating, it is the same thing that we said with the proteins. We force them to go up to a higher state. We're going to go in details in person when we meet, and also the next Thursday. I think that we should have covered all of this material, but we may need a little bit more time. Now, so let's go back. The question is, when do we stop that? All right? So the big question here is the following. Think, one criterion is the objective function. Starts from it. Critical. Why? Because what's going to happen to the objective function when you are reaching a lower point? Minimal changes, small changes. So one thing that you can do here is the tolerance, the usual thing, all right? So basically, it is the same thing with the gradient descent, all right? So basically we say, hey, if you find out that it does not change beyond, it does not change above this portion, you accept it, all right? Usually, if you're going to find it actually in also in your other studies, we accept something like this, right? This is roughly how it should be of the delta of the function should be at this range, okay? This is very, very important. It is used in most actually of the algorithms out there, all right? The other thing is when you have a number of iterations, okay? So you can actually do it for 1,000 times. Someone may say, wait, and what if it happens to 1,000 and 100? You know what you're doing? You have spent it a lot of time running experiments. You run the experiments for 1,000,000 repetitions. And when you find out, and you do it in many different studies and cases, so you have the experience to say, hey, I don't need 1,000,000, I need 100. Does it remind you something? Sure. When you do machine learning and you train something, the epochs. Exactly the same concept. Be careful. They're not the same thing, the same concept. What do? You run your system for 1,000,000 epochs to make sure that it reaches actually, steady state. All right? If it does not do this thing, you keep increasing the number or you change actually your parameters, of course. All right? But it is important to calibrate that because I go back to what I said. Your power is not to plug in numbers and give numbers. Anyone can do these things, right? Your power is actually to be able to calibrate things, all right? And this is very simple ways of doing that. Okay, so this is the second way to stop it, of course, is with a number of iterations, all right? You can actually have, let's say, you can do other things at these cases. As an example, you can stop when the objective function is less than a certain value that you can set, all right? Someone may say, why to do this thing? Because in many cases, we actually have practical criteria that we say it doesn't make any better to go lower than this, all right? Experience. The results are experience or physics, all right? These are the two things. The other possibility is that someone may do also the duration, all right, of computing. You may say, well, this is very weird, but they do have this option. And I think that even in Python and MATLAB, definitely, I know for MATLAB, it's sure that the duration of running is actually, included as a possible option. I don't know, maybe, Rishab, we need to ask Anukriti to check the Python, whether they have one of these criteria in Python also, which is the duration of this thing. Running.
Yeah, I believe it should be.
Okay, all right. You see, it's very weird, but someone may say, why? One of the possible issues that we have in this, one of the possible practical reasons is often you need an answer within this time. So whatever acceptable. Someone may say, but this is crazy. It is not, because the cost of achieving the global minimum versus a local minimum is very high for some reason. So therefore, it is better to find a minimum that works in 10 seconds rather than the global minimum in 1 hour. Think about these big differences, all right? So this is how it works. So there is on the internet, actually I tried to do it earlier. I was trying to do this thing that because maybe I created problems to the presentation. There is a very famous, not famous, that is one of the, if you go on YouTube and you type simulated annealing, you're going to find several videos that they show how the simulation, how like they take a ball and they let the ball fly down. All right, and they see how the ball does this thing. But the beauty of simulated annealing is that you don't have one sphere or one ball. You can have thousands of them. So in many of these examples, and I was trying to put it as I said for you to see it, is that, so this is mountains, ridges, and so on, all right? And you want to find out the minimum here. So what you do is that you create, a grid. And on this grid, you have, let's say, 1,000 spheres. And you let them come down, and then you monitor each one of them individually. What's going to happen? Can you imagine? This is the probability we discussed. Okay, so probabilistically, think probability-wise, all right? most of the spheres, where are they going to go? The minimum, to the global minimum. All right. This is the central assumption of how they call it, of this algorithm. But I may actually trick. This is not the grid thing that I made you. It is not a good idea. Forget about this grid, that they are all in a uniform position. You can actually randomize even throwing balls in the air. Right? Think it is like how to say, you have a hand here, all right, or you have here a pipe, and then it throws balls, all right. But the extent, the distance that you're gonna throw them, it is determined by your distribution. So, nevertheless, at the end of the day, if you send sufficient number of balls, the vast majority of them, they will go at the bottom. This is how it works. And there are several nice, how they call them, presentations on YouTube, all right, to show this thing. One of them, however, is a very interesting, tricky thing, that it seems to me that they have missed part of the code of the process. Remember, what is the process? Is that we give energy, or we give temperature. We excite the system to a higher level, all right? And then from this high level, we change the temperature. And as we change the temperature to a lower one, all right, with a particular schedule, okay, of changing the temperature, then to accept or not this state comes from a probability, and this probability is nothing else, but it is the distance that we have from the previous, all right? So the energy, all right? So what happens is, and then as you do this thing, eventually you cool down to the minimum. But it is very important for efficiency reasons to keep track of the, in quotes, best solution. Apparently, in this actually thing, they do not actually keep track of the best solutions, and they are true random. So that because you can see that the same position, it is actually, how to say, repeated several times. Very, very beautiful, actually, to see that. I couldn't put it on. Let me try it once more. Maybe, yeah. I'll try to do it in class, or next time I will start from my desktop instead of and try to see maybe it works, all right? But I can send you the link. It's not a big deal, actually. It's very, very beautiful. You know, let me tell you how to find it. Very, very easy. I don't know if FreeShub, no, don't bother, because we may waste too much time to link it. I'm actually, you wouldn't believe it, but I am on YouTube trying to find out how they call this thing. Yeah, actually, I don't even know how to run YouTube. Just a moment, please. We press this button here, YouTube, and then here you type simulated annealing, and usually I misspell things. So there are several presentations. Come on, where is this thing? Simulated annealing, grains of sand. No, 3. They have a lot of things. So they try. Okay, there it is. So the guy who did it called Andreas Müller. Okay, so probably a German guy. It is beautiful because it shows. Yeah, actually, I started it. Sorry. Okay, so it shows exactly this thing. So what it has is that it has, let's say, a ridge, and then from a position they send spheres. All right, and you can see that the spheres, they go down, but at the same time they go up. It's the beauty of giving higher temperature. All right, and then at the end, all of them, they will actually combine in a single location. All right. Now, one of the problems that we usually have used in the past as a demonstration, it is actually to try to solve the famous traveling salesman's problem. All right. And I bet that you can find many of these things. Okay. So if you what it does, you will see that the algorithm, it will try to create all possible combinations, all right? And as it does this thing, at the same, it is going to start actually, and it will give you the best solution. But the beauty is that you can actually also monitor at the same time the step size. So this is, remember that in the gradient descent, as we are approaching actually to find the solution, let's see what happens. it is the same thing, all right? The gradient descent, the step size becomes smaller and smaller and smaller. The same thing here, all right? So the step size, as the step size it becomes smaller and smaller, all right, then the accepted length of jump becomes smaller, all right? So this is how it works, okay? Now, if you actually go and you do the probability, if you go and you increase if you start actually and increase the steps, all right, the temperature slowly goes down, right, as you increase the steps. This is basically how to say the schedule of your system, how it works, all right, to eventually reach the best solution. Then it will stop when you have a certain, how to say, condition where, let's see, the certain things is the following, is that this, as the steps goes, it's gonna go like this and becomes steady state. And this guy here, the temperature goes down, 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 down until you reach the point of zero temperature. All right. Be careful. This is in Kelvin. All right. This is a special degrees that we go to absolute zero. When you reach absolute zero, then your system has stopped. Right. It cannot do anything else. This is how the Boltzmann distribution works. Anyway. So that's all, folks, the thing as an introduction to simulated annealing, all right? We use simulated annealing in order to optimize proteins, drugs, design coils and antennas for radars or for application of energy to destroy tumors. So it is a very powerful method, far more sophisticated than the gradient descent, right? But also, it is only good for certain things. Like I can give you a simple reason: duration. All right. In many cases, like I have not used, and I have not been aware of anyone using simulated annealing in training a machine learning algorithm. Rishab, you are more familiar with me. Have you heard anything about from this? If you're around,
I'm here. Yeah. Sorry, what?
You have or you haven't?
Not
Have
really
you heard?
that much.
And are you a fan? Not really. And I bet that we can check it again. I will actually check it because on Google. Last time that I did it, maybe months ago, like a year ago, I can say, nobody was using it in machine learning. All right. And machine learning is in fashion, guys. So therefore, but because you don't hear much about these things, a couple of years, machine learning will not be in fashion. They will, optimize it and they will just sell packages, and then they will go to other solutions. All right. So let's go back. So therefore, simulated annealing, guys, it is used for designing of antennas, for designing of new drugs, of proteins, of all of these kind of things that are a little bit outside of the applications of the type of how many red shoes were sold yesterday. All right. So yeah, make this joke primarily because actually not a joke. It's like a statement trying to alert people that there are many more things out there than just analysis of financial data. All right. Anyway, questions. I know that it is a little bit. This is the most difficult subject that we deal, and it's a bit outside of our background. But we are going to work on this thing, and then we are going to have sufficient, I hope, time to do the final thing, to do some on the generic algorithm again, how to select and optimize things. All right. But what I'd like you also, folks, to gain is to realize that the essence here is that all of these methods have many things in common. You have to reduce something. Second, while you do this, to have to adjust your steps. Third, you need to make decisions on the fly about something, accept or not, go that way or the other way. All right. Again, don't think that gradient descent is the panacea, but it is a solution. However, even there you do a choice immediately by selecting whatever gradient goes downhill. All right. So think. All right, that it is the same criteria. You do have a decision. All right. However, as many things, as we go deeper to these things, what we have found out is that more important actually is the cost function that you are going to use. What you want to optimize, all right? This is far more important than anything else, okay? So we can design, as I said, antennas for radars by selecting the appropriate target. The cost function is the target, all right? So this is the most critical thing. There are hundreds of algorithms out there to minimize something, guys. If you don't, however, have the appropriate thing, your work goes nowhere, all right? Remember that. It's not the layers, as we say with RISC-Hub sometimes, all right? But it is actually the data and what you want to achieve. All right, so that's all, okay, for now. What I want you to do, just read Simulate Annealing. Start from steps by step. So next time, we can actually go through this thing again in person and being able to actually do, how to say, specific examples, all right? Like to go through them, being able to follow the algorithm. We're going to do one session of next Thursday on the algorithm itself and how to run it. Okay, this is very, very important. Okay, to make sure that you understand the algorithm and the schedule and how we change the T and what is the effect. And then after this thing, I think you will be confident enough in order to use it in the future if something happens. What I urge you to do as you study simulated annealing is to do a comparison between gradient descent. Not if it is the same. I mean, it's not the same, it's different. However, I would like you to start appreciating the common things among them, because this is the essence of optimization. Okay. I think that I should rest this thing for now and open to questions on any concerns. And also, RISC-Hub, are there any things?
Yes. Can I give you a quick call on Viber? Just need to discuss something of the class before I make announcement.
Yeah, of course, sure. Okay. It's not an issue, but for the class, anything for the class?
Yeah, it is for the class. It is for the class. I'm just going to give you a call.
Yeah.
Dr. Checkers, I also have the announcement. So the code for the plot functions is available. It is in files. If you go to general files and then extra materials, there's a document called graph functions. So there you can find the function code for both MATLAB and Python.
So I need to understand you guys. I think she sent me an email. Can you send them an email or actually is it?
I have already posted on Teams.
Thank you for
But I just wanted to announce in the class just in case they don't check the post.
Yes. Important thing, folks, and Anukriti, I want you to verify that indeed we are providing the correct thing. So in assignment that you have right now to do on gradient descent, what I want you to use to present your data, as well as to have it with you to learn, all right, is the following. It is a function or a piece of code that it will allow you to take your function, let's say x squared plus y squared, or x squared 1 plus x squared 2, whatever. All right, it's irrelevant. And then plot it in 2D. So this is a 2D. So this is x1, x2, or omega 1, omega 2, or x and y. Be careful that your function is not a y anymore. It's an f. All right. So, and then this is contours, correct, Anukriti?
Yes.
So therefore, okay, it is not such a simple function, but the function is like this. But why to do that? Because then, and Anukriti, they should be able then to plot. If you start from this point here, it plots the steps that your algorithm does to find out the minimum. You got it?
Yes, that's what I've given them.
Excellent. Thank you so much.
So the only thing is, I have given them the actual function that will plot it, but the entire logic of which points to pick and which points to plot, they have to do that, because that's a part of the whole gradient descent. Yeah.
Yes, definitely correct.
Yeah. But I have given them the individual functions that they can use to one to plot the contour and then the other one to plot the points on top of the contour.
Excellent. Thank you for doing that again, guys. All right. So again, remember I told you I don't want you to, the purpose of the class is not for you to learn how to create functions and this stuff, rather than to use them at this case, because priority Why again we want to do this thing? Because in one of the questions I'm telling you is that I want you to make the thing unstable. I want to make gradient descent to fail. And how do you do that? By selecting a larger lambda. So the idea is that instead of doing this tick, tick, like this and finding the center, eventually this is going to do this thing and going to fail. It goes nowhere. And it is very, very important to see that visually, to understand it, all right? Also, for people that they have an interest, all right, you can actually use this as a way to better understand and appreciate, how to say, reaching the functionality, like how many loops, what is the trajectory, all right? And if I were you, all right, I would this actually do it by myself. I did it before I verified the algorithm for the assignment. I did it actually myself because I found it also intriguing. I think weird functions, all right, in order to see how weird functions for the functional minimize, all right, this thing, like add exponential, add cosines, add whatever stuff you can come up and see how the function looks like and if there is a minimum and how the algorithm would behave. So whatever assignment, guys, I give you, it cannot cover sufficiently any subject. It is you should search, period. And because you are graduate students, it is your job, truly job, all right? So therefore, when you go home, yes, the assignment can give you to have the code, but if you have done the correct code, from now on, you can test whatever two-dimensional you want. And of course, you can expand it to n dimensions, all right? That's it. But focus on the assignment, play around, do it, keep us in the loop. All right? If something is unclear in the assignment or the thing offense, because we write it one way, someone may email us in order to fix it to the other people. It's very important to do as fast as possible, as soon as possible. Any other thoughts from you guys? Any questions? No. All right. Great. Anukriti, thanks for doing that. If there is nothing else, I can hang up and Rishab, do you want to discuss something, sir?
Yeah, it is related to class. So let me give you a call and we can stay on the class for a few minutes.
Call me in a few minutes. Guys, if there is nothing else, again, please go and spend time reading about a simulated annealing. It is very simple. The tricky part is tricky. The new thing for you is the add of the probabilistic element of the Boltzmann distribution and the schedule of the temperature reduction. That's all, right? There's nothing more different. And then understand that, and next time you will see it in action.
Dr. Chekos, can we please stay on the class for a few minutes? Let me give you a call and I want to discuss the announcement before I make it.
So you want okay to get it. So you are going to call me on the phone, all right?
Yes.
But should I mute the class? Or actually,
yes,
I can hear you.
yes. Yeah, we need to mute the class.
I need to find out where the mute is. Okay, guys. But I can hear you. Any questions? Let me know. All right, folks. By the way, please bear with us because Rishab wants to do an announcement. I'm lost. I don't know what happens, but okay. So. Rishab, if you can hear me, call me, please, because we cannot keep the guys for.
Yeah, I'm calling you. I'm calling
you
right.
Okay, so remember that one of the problems, an interesting comparison is between greedy algorithms and here. I need to talk to you just a moment. Sorry. Ladies and gentlemen, so Rishab is going to provide you some specific information and a decision about the reports. For the reports. Rizkat, can you hear me?
Yeah.
Okay.
Yes. Hey guys, so I did go through your submissions, your progress reports, and there are a lot of people who have not submitted the report in the correct form. I took a complete lecture on what needs to be submitted and how it needs to be formatted, how you guys need to do references, how you guys need to do figures. So somebody who has attended that lecture and has submitted the correct thing, there is nothing else for you to do. For others, we are allowing one more day, that is till tomorrow 11:59 p.m. to correct your reports and submit it. Whatever you guys will be submitting right now in the progress report, combined with your final project, will be counting towards your grade. And in that in-person lecture, everything was explained, where the points will be deducted, what needs to be done in references, what needs to be done when the references are related to websites and everything. So if you haven't attended that lecture, please find somebody who did and ask them how to do that. But we are giving you one more day to prepare, correct your reports, do it in the way that we need it so that you don't lose points. Over to you, Dr. Checkers.
Okay, that's it, guys. Yes. This is the class gives you a lot of freedom, actually, and in regard to how to do things. All right, you're not with someone after you continuously, and that because to me it is frustrating if you don't comply to very specific and few things that we request from you guys. All right, but you're fortunate that the TA is willing actually to this thing because it was his effort. Give one more time and he will contact you, also email you who are the people who need to update these things, right? But come on, it is part of the whole thing actually to follow up with regulations. All right, anyway. So, any other questions? If not, we can actually have a nice time and enjoy the rest of the weekend and study. All right, so let us know if you have any more input. All right, any questions offline. All right, bye-bye, have a good time, enjoy.
Take care, everyone. Bye-bye.
Bye-bye, guys, bye.
Thank you. Bye.
Thank you.